considering the superposition of electromagnetic waves. Okay. So till now what we have done, we have considered only a monochromatic wave, rather we have considered a single wave of a single frequency. Okay. So before going ahead, let's look at what kind of things we have considered. So we have described, okay, so the waves, EM wave was what we have considered, so those were the plane waves, is it? Okay. So let's consider this kind of thing. Let's say you are having this wave. So if I am having E as some 0, some E naught 0, okay? Okay, let me write this way. So we consider this kind of wave. So like E0, E is for I, okay, so A dot R minus omega P, is it? Okay, so what is the B? So these were the fields we have considered. So the monochromatic waves we have considered. Okay? So now if I write this E0, since E0 is a constant vector, it simply specifies the direction of this E. Okay? In which plane this E is oriented. Okay, so let me write this E0 as like this 0. Let me write some constant number E naught and naught. Okay, so that means this electric field vector is where? Yeah, along y direction, and this B, let's say this is along, okay, let's consider it along z direction. Like this way, okay, and we consider the direction of the propagation of wave along x direction. Okay, so let's write it this way. So you are having this as the x direction and this as z direction. Okay, so this as y direction. I should have, okay, let me write this as y and this as z simply. Okay, so and this is x direction. Okay, now tell me what is the direction of the propagation? So where is the electric field resting? Electric field is along y direction, is it? So you are having the electric field along this direction and it will move. Okay, so let's take the real part of this thing, what you have. So real part of E will be simply what? So it is simply, tell me, E0, so that is actually along y direction, E0 cosine of, since it is along the x direction, Ax minus omega t. So that means this very vector, this electric field vector, will oscillate in time. Once it will propagate, but it will be fixed only in one direction, is it? So it will go like this thing, in only in one direction, this way. Clear? So what about the magnetic field vector? What about the magnetic field vector? So it's actually here. So you will be having like this thing in this very plane. So these vectors will be always perpendicular to each other. Is it true? So once the wave will propagate, so E will be always in that plane along y direction always. So we call this wave as a plane polarized wave because the field is restricted to one plane. Okay? You got my point? So this is actually this kind of thing, this kind of plane along which the field vector is. So conventionally we take, it's simply a convention, we take electric field vector as the polarization vector. Okay, it is simply the convention. But you can take, okay, you can call magnetic field to be the polarization. Okay, so when you take the polarization of the light, it implies magnetic field vector is also there, but these are aligned in certain plane. Since E and B are always perpendicular to each other, you align, let's say, electric field vector in one direction. Okay, so the magnetic field will get restricted to the perpendicular direction, and it will flow always in the same direction. Clear? So it will not change the direction. So it will always remain in the plane. So then I can say the wave, the plane wave that is represented by this kind of fields. Okay, let's say we call it as N plane polarized wave, is it? And the polarization is along. What is the polarization along? Y direction, is it? Because I am saying polarization vector to be the electric field vector, so the electric field vector is along Y direction. It is restricted in the Y direction. Clear? Oscillations of this electric field vector are restricted in this very direction. Clear? So this is how we define the polarization. Okay? So now let's take the more general situation. If I take now the superposition. So if I take the superposition of the waves, is it? Let's say of different, different wave vectors and all those kinds of things. In general, I can arrive at a different kind of polarization. Is it? So let's superimpose two monochromatic plane waves, which are linearly. Let's think two polarizations, which are two polarized waves, two linearly polarized waves. Let's superimpose them, and try to figure out what we will get. In general, we will be getting what we call the elliptical polarization. It will depend upon the phase difference between two waves. Okay, if you are having two waves, how you superimpose them, the superimposition will depend upon how you choose the initial phases or how you choose the phase difference between the waves, is it? Okay? So if there is no phase difference at all, you will get back what? The plane polarizer. If there is, let's say, some pi by 2 kind of phase difference, you will say it's actually the circular polarization. If it is neither of two, so it's in general elliptical polarization. We'll see it. Okay? So let's take what, and we'll see the meaning of these things, what exactly these things mean. Okay? So let's write, let's call some unit vector E. So let's describe, let's take some basis or some vectors E, okay, some unit vectors E, okay. So let me define two unit vectors, E dot E is equal to 1, and I am having another unit vector F, okay. We consider, let's consider two orthogonal unit vectors E and F, okay, which are orthogonal to direction of propagation. That's n. N is the direction of propagation. We have defined that. So what it means, f dot f is equal to 1. So you are having this E dot f that's equal to 0. And also we are having this n dot n, it's equal to 1. It's a unit vector. So you are having n dot e that's equal to 0 is equal to n dot f. Clear? So it's a three-dimensional coordinate system, you can think. Okay, so once one direction is the E direction, another is F direction, and another is N direction. Clear? Okay. So now let's take a superposition of two waves. Okay. So let's consider this kind of superposition. So we'll restrict ourselves to E. Okay, because I told you. So once E is fixed, B will get fixed automatically. Okay. So let's take the superposition of two waves. So let's call E0. So E0 is some complex constant, okay? A wave, let's consider a wave along E direction, okay? So that I will write E0E, okay? So E0 is some complex constant, you call it as a what amplitude of the wave, is it? So you can then write E raised to I k dot r minus omega t. Okay, then I will take another wave with amplitude, let's say E naught, so that's in the F direction. So is this the superposition of two plane waves? Is this a superposition? So we, okay, so this is a wave along, let's say, E direction, and this is where? Along the F direction. Clear? So now, so if you choose, let's say, E0, okay, so everything will depend upon how you choose the phases between the two waves, is it? So how you choose these E0 and E0 tilde, clear? Or E0 prime, how you choose these two constants or two numbers, so that will determine the polarization of the wave. Clear? So, you got my point? Okay, so let's take, so and B is how we determine B, so that is simply this n cross, okay, so n is the direction. Okay. So let's take, okay, if E0 E0 tilde are chosen to be a real, okay, or have the same phase, that is E0 by E0 tilde are real. So in other words, if they are real, simply, if they are the real things, so then what will be? So we are having plane polarized wave. Simply, so either the electric field vector will be in the up direction or in the down direction. Clear? So it is the same thing. It will be simply, let's say E0 is same as E0, so it will be E plus F. Okay? So simply the sum of two linearly polarized waves, is it? So that will again give you the linear polarization. Clear? But now let's choose these to be this way. Okay, let's choose. You will see in a moment actually what I mean by that. Okay. So let's choose this thing. E0 is equal to plus minus I E0 tilde. Let's choose it this way. Okay, what does that mean? So it's actually E raised power plus minus I pi by 2 E tilde 0. So that means phase difference between these two vectors is how much? Pi by 2, is it? Clear? Okay, now let's substitute it there. So what you will get? You will simply get this E vector to be equal to this E naught. Okay? So it is E plus minus I F E raised power I K dot R minus omega. Is it? So clear? You got my point? So what this is? It is actually again the linear sum, but it comes with an I sign here. Okay? So let's simplify it a bit with an example, then you may understand it. What exactly it means. If you see, it is actually okay. Now if you look here, it's actually x plus iy type. It's like this thing, a complex number. Z is equal to x plus iy. What it defines on a two-dimensional plane. Let's say mod of z square. If I take, what it will define? It will simply define with a circle, is it? So much on a two-dimensional plane it will define. So then you can see immediately. So this should represent to be what? A circle. That means this electric field vector, once it travels, it will traverse a circle. Okay? So you are having, let's say, field vector this way, so it will move on what? On a circle. So much on? So you will be having, let's say, a circle. Okay, so this is, let's say, the direction of the propagation. So it will either move this way or it will move the other way, clockwise or the anti-clockwise. This electric field vector will go as a circle. So that means, so it will move like this thing. Okay. So if you see, it will go. So you are having one circle, then the another circle, then the another circle, then the another circle, and so on. Clear? So this electric. So you can think. Let's say this as the origin. So you are having this as the electric field vector. So this electric field vector is like this thing. So it will move on this kind of trajectory. Clear? So that means this kind of wave will represent what? A circular polarized wave in general. So let's take, let's specify. Let's take the direction of propagation to be the z direction. Okay, let's take so this to be the z direction. And so since I have specified my n, is it? Now I have to figure out what E and F is. E and F are orthogonal to n, is it? So a suitable choice will be, okay, so you are having this as the propagation direction. Okay, so which implies I can choose this E. Let's assume E is along x direction and F is along y direction. Clear? So then this is a, they are all orthogonal, is it? So much E, F and N, they are orthogonal to each other, is it? And they are unit vectors. Clear? So now let's write it here. So what you will get, so E is equal to, okay, now tell me. So let's figure out, okay, so what it will be. So let's figure out EX. Let's figure out EX. What is EX? Can you tell me? What is EX? Okay, wait a second. So what is the physical field? Tell me what is the physical field? So the real of this object, is it? So I need to take the real. Okay. So E naught I will consider to be the real. So this is an A plus IB, and this is also A plus IB, is it? So tell me, what is the real of E? So it is simply E naught. Okay, then you are having vector E, then you are having cosine of K, since now it is along the Z direction. Let's take KZ minus omega T. Then I am having one more factor. So it is then I, so I and I will become minus, so it is F sine of Kz minus omega T. Is it? So there will be now, so this is plus minus. So you will be having like this thing. Huh? Clear? Is it true? Because I have got, it is plus minus. Huh? So when you take the plus sign, you will be getting what? A minus sign. When you take the minus sign, you will get a plus sign here. Okay? So now let's take the components here. So what is EX component? EX component, I mean the real component. Okay, what is EX component? What is E? So it will be simply E0 cosine of KZ minus omega T. What is EY component? E0 sine of, okay, plus minus KZ minus omega T. So now, sorry, EX. So let's square the two and sum. So EX square plus EY square, that is simply equal to E0 square. So that means the magnitude of this electric field vector remains constant during its propagation. Is it? So much on? So this is very important point. The magnitude of the vector should remain always what? Fixed. So much on? The electric field vector, it will remain always fixed. Okay. Now what is this equation? It is the equation of the circle. Is it? So that means it will traverse what? A circular track. Now you are having two solutions, two possible ways, is it? So one is the plus sign and another is minus sign. So it means this wave will either move in the anti-clockwise direction, the field vector will rotate along a circular track along the what? Anti-clockwise direction, or it may move in the clockwise direction. So these two represents actually two polarizations, circular polarizations of the wave. Clear? Got my point? Yes, we call actually, since it is actually the rotation, if you see, it's actually the rotation of the field, either the anti-clockwise direction or the clockwise direction. So when you measure the rotation along the direction of the propagation, okay, we call it as the helicity. Okay? So rotation means actually the angular momentum. If you are measuring the angular momentum, okay, here it is actually the spin angle, forget about spin. So think only the angular momentum because it's rotating. Vector is rotating, is it? Field is rotating. So when you move actually in the anti-clockwise direction, so you are actually moving along the direction of the wave. So that is, we call it as a positive helicity state, or we call it as the right circular polarized wave. Samajh aawa? And another case is if when you move actually in the clockwise direction, you will see what? Yourself moving backwards, or you will see actually moving against to the direction of propagation, is it? So when you are moving in the circle, it will come like this way, is it? So that means the direction of the rotation and the direction of propagation are opposite to each other. Clear? So we call it as a negative helicity or left circular polarization. Clear? So you are having two helicity states of an electromagnetic wave. One we call it the positive helicity wave, that means right circular polarized wave, or negative helicity state means left circular polarized state. Clear? Got my point? Okay. So now let's take, okay, in general, so we are having two cases. Two cases we have seen. When you are having this E0 same as E, okay, E naught, so you are having linear polarization, okay? Okay, then you are having the circular polarization. Now, in general, you can be, if the phase is either not 0 or pi by 2, so then you can be having what we call the elliptical polarization. Elliptical polarization means, so this very vector, so you are having the field vector, let's say E, it will traverse actually an elliptical trajectory. Okay, it will move actually along an ellipse. Clear? So now let's take an example. Okay, so you are having this very object. So E is equal to, what was it? So E0 vector E plus E0 filled in vector F. e raised for I k dot r minus omega. Clear? So let's take it moving along the z direction. Okay. So let me choose now. Let's choose this. Since E0 and E0 tilde, they are in general what? Complex numbers, is it? So let's choose this E0 to be, let's say A e raised for I delta 1, B e raised for, let's say I delta 2 and 0, sorry, delta 1, and E0 tilde, let's write. So let me check what is the notation I have used. Okay, like this thing. Let me choose this one. Instead, let me choose this E to be. So let's choose this E to be in this way. A e raised for I delta 1, B e raised for I delta 2, 0, e raised for I. Since wave is propagating along z direction, so we can choose it in this fashion. Can we do it? So what is your E vector? E vector is 1, 0, 0. And what is your F vector? 0, 1, 0. Okay, so I can put combine them in a single vector. Okay, so like this thing. So I have chosen them. So these are actually delta 1 minus delta 2 will represent the phase difference between the two waves. Clear? So, samajh aawa? You got it? Okay. So now let's write. Okay. So tell me, what about the nature of this very wave? Will it follow an ellipse? Okay, now let's try to figure it out. Okay? So let's try the real and imaginary parts. Okay? So let's try. So what this is? A cosine of delta 1 plus, okay, I sine of delta 1, and this is B. So this is cosine of delta 2 plus I sine of delta 2, then 0. Okay, so it's small e raised for, so it will be actually cosine of Az minus omega t, and then you are having plus I sine of Az minus omega t. So what is your Ex? So let's write a real part of the Ex. Okay, let's write. So this will represent me Ex, and this will Ey, and this is Ez, is it? So now let's write the real part of Ex. So real, okay, real part. So Ex, what is that? Tell me. So it's A cosine of delta 1, okay? Then cosine of Kz minus omega t, is it? Then you are having this I, and so that will make minus. So it's A sine of delta 1 sine of Kz minus omega t. So this is a real part of the Ex, and let's take Ey, what that is. So it's B cosine of delta 2 cosine of Kz minus omega t, okay, minus B sine of delta 2 sine of Kz minus omega t. Clear? So now let's write, okay, so let's write this divided by this objective, what that is. So Ex by this thing, okay. So let me write Ex by this thing and square, okay, plus Ey, this divided by this thing and square, okay. So summation like this thing. Let's call this as alpha, okay. Let's call this as beta, this entire object, okay. So let me write this way. So Ex square plus alpha square plus Ey square plus beta square. So what that will be equal to? Now 1 plus 1, that's 2, is it? So that will be 2, clear? Because it's 1 on this side and 1 on this side, clear? So it's 2. So that 2 I will divide here. So I will put it as 1. So 2 I will absorb within the alphas, okay? Now tell me, what is this alpha square? Now tell me. Now it will be twice that figure. A cosine of delta 1 cosine of Kz minus omega t minus A sine of delta 1 sine of Kz minus omega t whole square, is it? And similarly, what is beta square? That is twice b cosine of delta 1, sorry, delta 2 cosine of kz minus omega t minus b sine of delta 2 sine of kz minus omega t whole square. Okay? So what this equation is? Equation of an ellipse. Okay? So that means, so in this case, so this will represent actually an elliptical polarized wave. So you are having now three types of polarization, or in general you are having actually the elliptical polarization. Out of elliptical polarization you take two cases. One is the circular polarization and another is plane polarization. Or from the plane polarization you can get the circular polarization, or you can get the elliptical polarization. Got my point? Okay. Any question to you now? Okay, so I have asked you to go through the this book. I mean Gattek's polarization. So part. So there is a chapter, polarization and the double reflection. You should go through that very chapter, okay, thoroughly. Okay, so you will understand then how we can create experimentally the polarized waves. You got my point? So you will understand there different kinds of prisms, which are different kinds of instruments which are used for creating the polarized light. Clear? Okay, so that will be the assignment for the people. That is simply the review. Okay, so let's move back towards this. Okay, so we have constructed actually E. If you see, so all this E, so you are having this very object by x equal to 0, nebula square B, and then you are having this nebula square A. So A also satisfies the same equation, is it? Clear? So now when I take an electromagnetic wave, I will specify the polarization of that very wave. Clear? So we have done now, you can be having the polarization of the waves. Previously we have not used any kind of polarization vector associated with the wave, is it? Now when I write the solution of, let's say, of any kind of this equation, let's say if I write E field, so I will specify the polarization. Since we are using the potential formulation of the theory, so I will be using this kind of equation. Okay? So what was the form of this E? So E is actually in general. So it's E raised for I k dot R minus omega t, is it? So what will be the form of this A? The same, E raised for I k dot, is it? So much sure. So let's write the solution for the monochromatic wave. So you are having monochromatic wave, rather EM wave. So let's write it in terms of this potential A. So let me specify some A as an amplitude of the wave. Okay, let's write A, some kind of amplitude. Okay, let's write E vector to be the polarization vector. I will consider linear polarization. Okay, I will start from the linear polarization. Okay, so let's say E to be the polarization vector, a linearly polarized wave. Okay, and then you put E raised for I k dot R minus omega t, is it? Clear? So this is our wave. Is it the solution to that very equation? Now I have specified the polarization. Okay, so you could have put, okay, so this A can be in general a complex number. Okay, is, okay, the way we wrote E is equal to, if you remember, we wrote E is equal to E0 like this thing, is it? This E0 we considered in general complex. It's actually the amplitude of the wave, is it? So similarly, I can consider this A to be complex in general, is it? So now if I need to figure out what is the, okay, so E specifies that, right? E specifies the polarization. Polarization. Here we consider linear polarization. Polarization. Okay. Clear? Got my point? Okay. Now the point is here, when I try to figure out the physical field, what I take? since if I need to figure out the electric field, is it the real case? I mean the physical electric field, that means the real part of the electric field vector, is it? So I need to take the real part of this very equation. Okay? So there is another way to write it. If I add, so this is in general a complex, is it? So if I put its conjugate to this thing, let's put a conjugate to this thing. Okay, E0 star, that's right, e raised to minus I k dot r minus omega t. Let's put its conjugate. Now tell me, is E now real? So E is now real. So I have made this quantity to be real, putting just the conjugate. You got my point? Similarly, if you are having A, this is a complex number in general, I want to make this A real because I need to figure out the field, is it? So we know in Coulomb gauge, so E is equal to minus 1 by C partial A by partial T. If this is a real quantity I am looking for, so I want this A to be real, is it? For that matter, what I will do, I will put a complex conjugate. So A star E vector e raised to minus I k dot r minus omega t. Clear? So this is our A. So but it is just for one polarization, is it? Okay, now if I superimpose these waves, what I have to do? So I can have a superimposition of different polarizations, different wave vectors, is it? And what is the relation between this k and omega? So omega square is equal to c square, this k square. Clear? So that means, so they are related to each other, right? They are not independent. Omega and k are not independent. Got my point? If you specify k, means specifying omega. If you specify omega, means specifying k. Clear? So they are not independent of each other. Clear? So now let's try to superimpose all these monochromatic waves of let's assume of different, I mean wave vectors and different polarization. Clear? So much since E specifies me one polarization. For that matter, let me take this way. Okay. Okay, so let me write this E. Okay, let me shift it, I mean rewrite it in this fashion. So lambda is actually one. Since I am having only two polarization states, whether you are having elliptical polarization or the circular polarization or linear polarization, you are having only two states. Let's say in linear, either up or down. In circular, left or right. In ellipse, the same thing, left or right. Okay, clear? So that's why I am having only two polarization states here. Clear? So let's assume you are having a wave vector k and some polarization lambda. Is it? So what will happen? So I can then superimpose all these very waves. That means for each lambda and for each k I will be having an A vector, is it? And now let's superimpose them. What does that mean? I need to sum them up. So how to do it? So I will write it in this way. So let's write this general superposition then. So let me write this A as for all these waves we are trying. So you will sum over these polarization. Let's say lambda is equal to 1 and 2. Since for every wave I am having a wave vector k, is it? That means I need to sum over this wave vector as well. Clear? Okay, so let me write first this thing. So for every wave you will be having this coefficient A lambda. Okay? And you will be having this polarization E lambda, is it? So let's put a k vector here. That means for every wave you are having a polarization E, is it? E lambda, and for every k you are having this A, this amplitude. Clear? So you are having e raised to I k dot r minus omega t plus. Okay, so you are having this A star lambda k. Okay, E lambda k. So this is actually in general complex quantity, yeah? Polarization, because we have just seen. So in circular polarization, what we have seen? E plus minus IF. Is that true? So that's why you should put actually a complex. That's it. So I k dot r minus omega t. So this is a wave corresponding to the lambda polarization or for the kth vector. Okay. So now what I need to do? I need to sum over all these waves. So that means you first sum over the polarizations and you sum over the wave vectors. So that means this momentum you sum over, because k is a continuous variable. So this is actually this represents you the superposition of these waves. So समझो? So for each polarization. Clear? Now is this now the superposition? And is A a real quantity now? Huh? True? Okay. So now this, let me convert this very object, since this is, I start with the linear polarization. Okay, now if you see, this polarization vector spawns a two-dimensional space. So it resides in a two-dimensional vector space. Is it? So how many polarization states are possible? For this very case, only two polarization states, is it? So how many dimensionality of the vector space then? What is the dimensionality of the vector space? If this polarization vector has only two possibilities, so what is the dimensionality? Huh? Two-dimensional vector space. It resides in a two-dimensional vector space. Clear? So that means so you can choose this E to be the basis. So if you see, it's actually the basis extension of a given vector, is it? So forget about this very objective. So you take the basis vector, multiply it by some coefficient. So how we do the basis extension of a vector? Or basis extension of some function. So if you are having some basis vectors E, so how you do it? So you write some f as sum over I, these ei multiplied by some number. Is that true? You got my, do you see it's a basis expansion? So that means you are actually expanding this vector potential, this vector, in a basis E. The basis is specified by here, the polarization vectors. Clear? So that means these polarization vectors specify E lambda k specify a two-dimensional vector space. Okay, I will not use Hilbert space. I will use simply the vector space. The problem is that actually for EN the norm is undefined for these waves. Okay, you got it? Now let's convert. Okay, so I can make a basis transformation. So if I assume this E lambda to be linear polarization vectors, then I can go to the circular polarization. So suppose if you are having two-dimensional basis, is it? So you are having two, these are two, let's say X and Y. Clear? So this is a basis set. So you can choose another basis set, let's say X prime and Y prime. Can you choose? So either you choose this basis or this prime at one. Clear? So now what is the basis? So you can be having a basis vector specified by the linear polarization, or you can be specified by the circular polarization. Clear? But it is most suitable to represent it in terms of circular polarization. Clear? Got my point? So for that matter, what I will do, I will change this basis. So okay, so how to do it? Okay. So you need to keep it as such, there is no problem, okay? So it's very simple. So let me define another polarization state, this epsilon, okay? So let's define this epsilon plus as, so E1 plus I E2 by root 2. So E1 is one linear polarization and E2 is another vector, okay? So how many values are for this E? So lambda goes from 1 to 2. So you are having this vector space. So E1 and E2, is it? So out of this very vector space, I can construct with the new vector space. Okay, or the new basis. Sorry, out of this very basis, I can construct a new basis like this thing. Epsilon, let's say new basis is what? Epsilon, okay? So what is the condition on this E1 and E2? So E1 dot E2 is equal to 1. Sorry, E1, E2 dot E2 is equal to 1. They are orthogonal to each other. This is equal to 0. So think of the x-axis and the y-axis, and propagation is along z-axis. Okay. So I can write this thing. So I can have epsilon minus another. So that is another possibility, like this. Clear? So what this E plus represent? This epsilon plus it represents the right circular polarization. Is it? Because we have just seen E plus I F, is it? So instead of F, I am having E1 and E2. So this is simply the right circular polarization. So that means this will represent the vector corresponding to the right circular polarization, and the epsilon minus will give you the left circular polarization. Now if you multiply, let's say, so let's put a vector on this thing, epsilon plus dot epsilon plus. You will see it is actually 0. So if you dot this epsilon plus with itself, you will see it is actually 0. Okay, now what that means? E1 dot E1, so that's 1. E2 dot E2, that's 1. And minus, is it 1 minus 1 is 0. E1 dot E2 is what? 0. Got my point? And similarly, if you are having this E minus dot E minus, that is again 0, and you will be having this way, E plus dot E minus, that is equal to 1. Okay? Got it? समझ आया? Okay. So now let's write them. So you can convert this E1 and E2, okay, in terms of, so what is E1 now? Can you tell me? So it's epsilon plus epsilon minus divided by root of 2. Is that true? What is this E2? What is E2? Just subtract it. So this epsilon plus minus epsilon minus divided by root of 2I. Clear? समझ आया? You got it? So you don't need to, okay, so for E1 and E2, you don't need to okay, expand this thing. What you will do simply, so ultimately when you sum it, okay, so let's sum over lambda and this 1 and 2. So it will be E1 and E1 star plus another term with E2 and E2 star, is it? So then you need to put E1 as that and E2 and cancel all these terms. Forget those things, you don't need to do that. So you'll simply replace this object by epsilon plus, okay. So epsilon plus, okay. So let me write epsilon lambda, and this lambda will go as now either plus or minus. So like this thing, and you don't need to do it. Okay, so just so it will turn out to be the same thing. What I am saying. Okay. So there will actually come in this very term a factor of I. So you absorb that with this A star. So because it's complex, so you can take the I within that. Clear? So it is the same thing. Now, so the formula should look the same thing, whether you put it in one basis or in the other basis. So now this is actually the your field in terms of the circular polarization. Okay, so that's why I have put as lambda equal to plus and minus. So you can write 1 and 2, then 1 and 2 will specify the circular polarization as well. Huh? So that means formula is the same thing. There isn't any problem. Clear? So now when the field moves, okay, the important, so this is the general superposition of the waves. Clear? So there is important thing, this k dot epsilon is actually, so because the transverse of the condition, so this is equal to 0. Where from it will come? Del dot A. So del dot E is equal to 0. Or even del dot A, because we are in the radiation gauge or Coulomb gauge, del dot A is equal to 0. So it comes from here as well. Okay. So now we have specified the polarization. Clear? So when that means when the field moves, it carries an angular momentum. Okay, so let's calculate how much angular momentum is carried by this very wave. Okay, so we need to figure out. So does it have a mass? Does it have a mass? So does EM wave has a mass? No. Okay, or in other words, photon does not have mass. We call the quanta of this EM wave as the photon, and it does not have a mass. Sorry, rest mass. When I say mass, it means rest mass. There is no other mass other than rest mass. Only the rest mass exists in the world. This kind of. So it is having no rest mass. So how we define the spin? The angular momentum for these massless kind of particles, it is defined by the helicity, is it? I just say talk this thing. Either the wave can move in the direction of the field, so that means this field vector will rotate in the direction of the field, is it? Or it will rotate in the opposite direction to the field. So that we call the helicity of the particle, or the helicity of the wave. Or in other words, let's try to measure this angular momentum of the wave, whether it's moving in the direction of the this propagation, whether you are measuring the angular momentum in the direction of the propagation, or you are measuring it to the opposite to the direction of propagation. Or in other words, let's try to figure out how much helicity an electromagnetic wave carries. So we need to figure out how much helicity is there. Okay, got it? So let's try to figure out. So first we start with the angle, because for defining the helicity I need to figure out what is the angular momentum, is it? Then we can measure angular momentum in the direction of the propagation. Okay? So everybody got the problem what we are trying to do? Huh? So any question till now? So how we define the angular momentum tensor? So now no noise, please. You want to stop here?